Well, I think the idea is to continue thinking outside the box in different directions, meaning
Well,
just like how the math allows us to think in multiple dimensions outside of our perception system, sort of thinking, uh, um, coming up with new tools of mathematics or computation or all those kinds of things to take different perspectives on our universe,
well, I'm
right?
all for that, and I kind of have even elevated it into a principle, which is of complementarity, following Bohr, that you need different ways of thinking, even about the same things, in order to do justice to their reality and answer different kinds of questions about them. I mean, we've several times alluded to the fact that human beings are hard to understand, and the concepts that you use to understand human beings, if you want to prescribe drugs for them or see what's going to happen if they move very fast or or are exposed to radiation, and so that requires one kind of thinking that's very physical, based on the fact that the materials that we're made out of. On the other hand, if you want to understand how a person's going to behave in a different kind of situation, uh, you need entirely different concepts from psychology. And there's nothing wrong with that. You can have very different ways of addressing the same material that are useful for different purposes, right?
Can you describe this idea, which is fascinating, of complementarity a little bit? Sort of, first of all, what stated as the principle? What is it? And second of all, what are good examples? Starting from quantum mechanics,
Yeah.
you still mentioned psychology. Let's talk about this more. It's like one in your new book, one of the most fascinating ideas, actually.
I think it's a wonderful, yeah. It's sort of, to me, it's the culminating chapter of the book, and I think since the whole book is about the big lessons or big takeaways from profound understanding of the physical world that we've achieved, including that it's mysterious in some ways. This was the final, overarching lesson, complementarity, and it's a approach. It's so unlike some of these other things, which are just facts about the world, like the world is both big and small in different senses, and is big, but we're not small. Things we talked about earlier, and the fact that the universe is comprehensible and how complexity could emerge from simplicity, and so those things are, in the broad sense, facts about the world. Complementarity is more an attitude towards the world that is encouraged by the facts about the world. And it's the idea, the concept of the approach or the realization that it can be appropriate and useful and inevitable and unavoidable to use very different descriptions of the same object or the same system or the same situation to answer different kinds of questions that may be very different and even mutually uninterpretable, mutually incomprehensible.
But both correct somehow.
But both correct and sources of different kinds of insight.
Which is so weird.
Yeah, well,
but it seems to work in so many cases.
It works in many cases, and I think it's a deep fact about the world and how we should approach it. Its most rigorous form, where it's actually a theorem, if quantum mechanics is correct, occurs in quantum mechanics, where the primary description of the world is in terms of wave functions. But let's not talk about the world. Let's just talk about a particle, an electron. Okay, it's the primary description of that electron is its wave function, and the wave function can be used to predict where it's going to be, and if you observe, it'll be in different places with different probabilities, or how fast it's moving, and it'll also be moving in different ways with different probabilities. That's what quantum mechanics says. And you can predict either set of probabilities. What's going to happen if I make an observation of the position or the velocity. But so the wave function gives you ways of doing both of those. But to do it, to get those predictions, you have to process the wave function in different ways. You process it one way for position and in a different way for momentum. And those ways are mathematically incompatible. It's like, it's like you have a stone and you can sculpt it into Venus de Milo, or you can sculpt it into David, but you can't do both. You can, and that's an example of complementarity. But to answer different kinds of questions, you have to analyze the system in different ways that are mutually incompatible, but both valid to answer different kinds of questions. So in that case, it's a theorem, but I think it's a much more widespread phenomena that applies to many cases where we can't prove it as a theorem, but it's a piece of wisdom, if you like, and appears to be a very important insight.
Do you?
And if you ignore it, you can get very confused and misguided.
Do you think this is a useful hack for ideas that we don't fully understand, or is this somehow a fundamental property of all or many ideas that you can take multiple perspectives and they're both true?
Well, I think it's both.
So it's both the answer to all questions.
Yes, that's right. It's not either or, it's both.
It's paralyzing to think that we live in a world that's fundamentally like surrounded by complementary ideas, like because we want we somehow want to attach ourselves to absolute truths, and absolute truths certainly don't like the idea of complementarity.
Yes, Einstein was very uncomfortable with complementarity, and in a broad sense, the famous Bohr-Einstein debates revolved around this question of whether the complementarity that is a foundational feature of quantum mechanics as we have it is a permanent feature of the universe and our description of nature. And so far, quantum mechanics wins, and it's gone from triumph to triumph. Whether complementarity is rock bottom, I guess you can never be sure. I mean, but it looks awfully good, and it's been very successful. And certainly, its complementarity has been extremely useful and fruitful in that domain, including some of Einstein's attempts to challenge it with like the famous Einstein-Podolsky-Rosen experiment turned out to be confirmations of that have been useful in themselves. But so thinking about these things was fruitful, but not in the way that Einstein hoped. So as I said, in the case of quantum mechanics and this dilemma or dichotomy between processing the wave function in different ways, it's a theorem. They're mutually incompatible, and that the physical correlate of that is the Heisenberg uncertainty principle, that you can't have position and momentum determined at once.